Generative design enables designers to work with a combination of computing processes and artificial intelligence to solve complex engineering challenges. Generative design, coupled with additive manufacturing, allows engineers and designers to create components or products which were not earlier possible with conventional design and manufacturing. In this episode of AM Infocast, we connect with Lin Kayser, CEO Hyperganic, to understand how they are using the power of artificial intelligence and computer algorithms to simplify the design process in additive manufacturing. Tune in as Lin talks about his journey in the additive manufacturing industry, Hyperganic's expansion plans in Asia, and the future of manufacturing.
Welcome, Lin, to AM Infocast, and great to have you here for today.
Thank you. Very happy to be here.
Lin, you come with 25 years of experience of driving disruptive technology ventures. How has your journey been with additive manufacturing and Hyperganic to be particular?
Yeah, as you said, I have been an entrepreneur for quite a long time. In 2012, I discovered additive manufacturing, like many people, through the MakerBot craze, lots of FDM printers around. Very quickly, I was fascinated by what was going on, not so much in the consumer space, but in the industrial space. 20 minutes away from our office in Munich is one of the leading companies in additive manufacturing, EOS. And I've gotten some really good insights, from these companies. What is really going on in the field of industrial additive, almost unbeknownst to most people. So I was really fascinated by this technology because I've been working in computer. I've been a coder all my life. Of course, I haven't coded a lot of applications recently. Stopped 15 years ago. But I started writing computer code when I was 8 years old. So I witnessed the entire PC revolution. And software for me was always one of the most creative things you can do. You can imagine something, and then you can build it, and there it interacts with you. So it's fascinating, and there are almost no limits to what you can do. But what frustrated me immensely over the years was, how much slower, in contrast to the information technology revolution that I was witnessing, innovation happened in other spaces. So, if you think about computer technology, 10, 12 years ago, almost nobody had a smartphone. 20 years ago, very few people used the internet. 30 years ago, the first PCs were around. Very few people used them. 40 years ago, all of this stuff was invented. So we've seen a dramatic curve in information technology, and most of this is, has been powered by Moore's law, exponential speed. So we are quite used to everything that is being touched by information technology is very, very fast, quite disruptive and quite amazing, actually, if you think about it. But if you, for example, sit in a 40-year-old car, it's actually not that different. And if you look very closely, the only difference between a car 40 years ago and a car today is basically the presence of screens and all of the things that are basically connected to information technology again. So I know there are a lot of things behind the under the hood, no pun intended, but fundamentally innovation has not been happening that fast. If innovation in transportation had happened as fast as in information technology, we would be all flying in cars, and levitating and flying to the moon and whatever, right? So there's a stark contrast between these two fields. And I realized that additive manufacturing is quite similar in its way to coding. So you code something and you can print it, and as long as it adheres to the laws of physics, it is actually buildable. And that fascinated me. And so I thought, maybe there is a way we can connect the speed of information technology to additive manufacturing to dramatically accelerate innovation in physical products. And why is that important? Well, we face a lot of challenges as humanity these days, and a lot of these challenges are engineering challenges. And I think that by using our approach, the Hyperganic approach, together with additive manufacturing, we can actually out-innovate some of these challenges. And so what is our approach? So one of the things that I think has hampered the adoption and the breakthroughs in additive manufacturing is that we're still feeding these printers with models that were designed using tools that were created for something completely different. So if you think about it, if you sit in front of a modern CAD computer-aided design application, it is essentially a direct descendant of pen and paper. 100 years ago, people drew a plan on with pen and paper, and then somebody would build the thing that they drew for them. Today, we do it in a very sophisticated computer-aided environment, but fundamentally, you're still sitting there. Your brain invents something, and then you put it on paper or you encode it into the computer using geometric primitives, but it's a very, very manual and laborious process. And so the idea that I had, and together with my co-founder, Michael Gallo, is how can we use the power of software, of a software paradigm, not an application software like a CAD system, but literally using code to describe objects. And that's what we're doing with Hyperganic. So the first couple of years, Michael and I, we were just looking at the basics. We created a completely new geometry stack, that allowed us to create objects that are almost unlimited in complexity. Why is that so important? Because once you have a computer design things automatically also become more complex. So we did that for the first couple of years. And then in 2017, we started the company. We self-funded it mostly. I mean, we had a big exit in 2011. We sold our last company to Adobe, completely different space, image processing for the film industry. And so we were able to self-fund for a really long time, took a little bit of angel money, but then earlier this year closed a significant seed financing round of 7.8 million and have been growing really fast. We had 12 people last year. We have 40 people here. Now at this point, want to go to 50 people and then triple again the company until the end of next year. So what are we doing? Hyperganic builds objects, physical objects, using computer algorithms and AI, and then outputs them in digital factories for mass production using additive manufacturing. And our paradigm is very radically different from the way you traditionally build objects. Traditionally, you design objects through a visual process. You create visually the object that you have in your mind. What we do is we create a logical representation of the object and then let the computer come up with the actual shape. And so the objects that we create are in a very, very broad range of industries. We're working with consumer goods, we're working in the medical field, we're working on aerospace applications. And it's been a blast. It's been a long time coming. You had to spend a lot of really significant work on establishing the base technology. But here we are now, year 2021, and we are building objects from code, and we are lifting all of this to a new paradigm that hopefully will help us dramatically accelerate innovation because we badly need it.
That's great. And that's a really interesting journey, and the problem statement you found in the industry to work towards it. And Hyperganic, as you said, is using artificial intelligence and algorithms to simplify the design process in additive manufacturing. So can you provide a little more in-depth insight behind this approach?
Yes, exactly. And I wouldn't so much say it simplifies it, it's just a different paradigm. So what we do is, when you as an engineer, when you create an object, you are also following an algorithm. I mean, it's not like divine inspiration. It's not like, somebody, you sit in front of your computer and magically a rocket engine, falls from the sky. No, I mean, you've learned how to design it. You have seen previous design. You have general principles that you apply. And we take this knowledge, this algorithm that the engineer, kind of intuitively follows, and we encode it in computer algorithms. Now it's a software approach, right? So it's not a visual approach. So at first, it's a little bit abstract, but people get it pretty quickly because, the logical parts of an object are also very often correspond to visual aspects of it. So it's very, very easy to actually connect that. So we take that, and then, using our novel geometry kernel, we can then generate interesting shapes and, connect them and grow cooling channels and can do all kinds of things. And the interesting thing about this approach is that a lot of this can get really generalized. For example, we had one of our aerospace engineers here at Hyperganic created a novel type of rocket combustion chamber for her master's thesis at the University of Stuttgart. And we were able to take some of the algorithms that she developed for routing cooling channels, across the surface of this rocket engine, and apply it to the medical field, where we need to grow capillaries that then are printed on a bioprinter, for blood vessels. So it is very interesting that some principles of engineering are pretty universal, and you can apply them in a very broad field. So what are we doing? I mean, we are basically working with our customers and say, okay, how would you design this objects if you did it manually? And then we move that to the computer. And now one very interesting thing happens. The computer, of course, never tires. The computer never wants to go home. So you can explore a vastly bigger solution space than if you did that as a traditional engineer. As a traditional engineer, you have one shot, maybe two shots, maybe three shots, maybe four iterations until you have to have a perfect object. So you will always kind of err on the side of it being a little bit over-engineered. So the objects that we have all around you and I, all the people listening, I challenge you to look very carefully at all the physical objects that you have in your room right now and think, whether they are truly optimal. Are they the perfect representation of what they should be? And, the answer very often is no. I mean, they are pretty simple. I mean, there's a tube, connected to a piece of wood, and we call it a table. But it could actually be way more interesting. And if you want to see something interesting, then you just look out in nature. If you look at a tree, if you look at a flower, if you look just at your hand, you imagine that machines could be way more complex. And what does nature do? Well, nature designs things not by plan, it designs it by accident, it designs it by evolution. And so when you move engineering into computer algorithms, you can start doing that as well. Not every object that you create needs to function perfectly, but if you generate 1,000 objects, you can pick the 3 that are hopefully going to perform very well. You can simulate, you can create feedback loops, you can print them and test them. And so you kind of emulate what innovation does in nature, what nature does with evolution for creating innovation. And that's a very, very interesting thing that's happening, is that the objects that we create are far more elegant, far more functional, far more complex, and far more sustainable very often than the stuff that you traditionally engineer when you have an engineer who has limited time and just wants to go home at some point.
Yeah, that's really interesting, the approach which you're taking at Hyperganic. And we understand from your past, press releases and case studies that you are working in application sectors like aerospace, medical, and consumer applications. Can you enumerate a few success stories which have been enabled with your technology in the recent past?
Yeah, I mean, one of the challenges that we have is that we are under strict non-disclosure agreements with most of the projects that we are working on. I can give you some examples, though. Yeah, I mean, for example, there is one field that is extremely important for the future of humanity, and that's the entire field of heating and cooling. So the Earth is getting warmer and warmer. We are all talking about climate change. We are actually going to be with Hyperganic at the COP26 conference in Glasgow very soon, to talk about some of these issues. Heating and cooling is one of the things that we need to actually solve. And heating and cooling takes a lot of energy, emits a lot of CO2, and it is incredibly inefficient how it's currently done. So we can now design heat exchangers. What is a heat exchanger? The tubes behind your refrigerator is a heat exchanger. A heat sink for a microchip is a heat exchanger. A AC system, air conditioning system, has a heat exchanger. So heat exchangers are everywhere. And by using these algorithmic engineering approaches, we can now start designing structures that are significantly more complex than you would ever engineer as a human. Now, why is that important for heat exchangers? If you look at heat exchangers, one of the things that they always need to balance is the amount of pressure that falls off when you push something through it. So in other words, the resistance, if I push air through a heat exchanger, ideally it goes through without effort, because then I don't need a big fan, to drive it. And the other thing is, of course, surface area. The more surface, it is exposed to the heat, the more heat I can also take away. And in traditional engineering, it's very hard to balance these two things against each other. But if you have an algorithmic engineer, you can explore a lot of really radical solutions. And that's what we're doing. And we are seeing incredible performance gains using these kinds of approaches. If you could just save 20% or 30% or 40% of the energy that currently goes, for example, into cooling of large server farms, you could really make a dent in global carbon emissions. If you found a way to build air conditioning systems that consume significantly less power, you could also make a huge dent in electricity consumptions, especially in hotter climates. And again, reduce the amount of electricity that needs to be generated, reduce the amount of carbon emissions immediately. So we're working on some of these things. Consumer goods, a lot of things that are going on currently. One of the interesting aspects of having a computer algorithm as an engineer is that you can generate objects automatically based on external data. So for example, we did some work with people who create bicycle helmets. I don't know if you have a fitting bicycle helmet. I have 5 kids. I can tell you, once a year, buying bicycle helmets for all of these 5 kids is really a very pleasant experience. Not. So we're trying to squeeze, one size fits all helmets onto people who have vastly different heads. So if you can start with a head scan and then grow the helmet algorithmically over that scan, you have a perfectly fitting helmet, and you can take the crash data that you get from bicycle accidents, which unfortunately also still happen, and feed that also into the algorithm and reinforce the helmet in certain areas. So for example, one helmet that we did a while ago was very strong on the sides, but at the top it was very transparent and let the air through, because people never fall on the top of their heads. They've always fall to the sides. You would have to have a really strange bicycle crash if you were to hit exactly the top of your head. So you can actually reduce the material, let the air go through, etc. So a lot of these kinds of things are happening. So I would say the sweet spot for our technology right now is 3 areas. One, because you have an algorithmic engineer, a computerized engineer that never tires, you can build objects that are far more complex than anything that has ever been attempted before. So this is very, very interesting for a lot of fields, especially in the medical field. You can build bone-like structures, but now you can use these bone-like structures also in other engineering fields. Very, very interesting. Now you can, I gave the example of heat exchangers, build really complex surface areas, etc. Very interesting. So highly complex objects is one area. The other area is customized objects, mass customized objects. So objects that are all similar, but every object is different, like the bicycle helmet that I gave as an example. So here you have an input, then you have an algorithmic process that automatically runs, and you have an output that then can go directly into production. So this is a field where we are very strong. And then the third field is basically the area where you need to optimize things to perfection. So instead of one object, you generate thousands of objects, you evaluate them somehow, you're testing them, you're simulating them, you're test firing them, whatever. And then you feed that back into the algorithmic loop and you improve upon. That's kind of synthetic evolution. And there you explore a gigantic solution space with lots of different parameters, and you search for one optimal solution. And that's the third area. So the 3 areas are highly complex objects, mass customized objects, and highly optimized objects. This is where we're currently shining, and these are where all the applications are currently located that we're approaching together with our customers. And our customers are all over the world, right? We have customers in the United States, we have customers in Europe, we have customers in Southeast Asia, we have customers in China, we have customers in the Arabic world, we have customers in Africa. So except for Antarctica, I think we have basically covered all the continents by now.
Yeah, that's great. And congratulations on the success you had in the short time since inception. And now, you are expanding into Asia with your first footprint in Singapore. What does your plans for Asia look like?
Yeah, I'm actually currently in Singapore. Very happy to have finally let in. Yeah, so the Singapore government allowed Germans, specifically Germans. I don't know what we did right, but specifically Germans were allowed in. If I were from Austria or Switzerland or France, I couldn't get in. So we have a wonderful office here in Singapore now. We have grown this from basically one person to 15 people over the course of the last 8 months. And we are super, super happy just because of the quality of people we find. Very well educated, very diligent, very, very good work ethics. And so we are looking to significantly expanding this office again, over the course of the next 12 months. And we see a lot of growth here just in terms of the staff level. Now, what do we do here? I mean, some companies open up offices in countries like Singapore, generally in Asia and China, whatever, to have a sales office there, to have a beachhead to enter the market. Now, this is of course, valid aspect of any venture that you do. However, we don't see it that way. We just look for amazing staff anywhere in the world where we can find it. And we look for alignment with the local market. And there's something really fascinating about Singapore. Singapore has identified additive manufacturing as the future of industrialization. So there are a lot of projects going on here. There's a lot of interest by the government to focus on these kinds of technologies. And there's a true willingness to move this sector forward. I have rarely seen something like that, because in Europe, something like that is very, very unusual. In Europe, innovation happens basically, it's driven by companies, and the government doesn't really do much, it doesn't steer much. In Singapore, we see the same thing. In China, we see some of this also in the Arabic states. The governments are very visionary in a way to establish certain technologies and certain paradigm shifts for their country. Singapore, for example, identified just at the beginning of their foundation the microchip industry as a very important future technology and industry. And I think 2 years after independence of Singapore, National Semiconductor actually built the first fab here. And Singapore is still one of the leading countries for building and exporting microchips. And they are doing this for additive manufacturing. So this is another good reason to be here. But the primary reason here in Singapore is really because we are just amazed by the quality of people we find. And we're super happy to have them integrated into our global team. Now, Asia in general, I mean, there is a lot of stuff going on. We have quite a few customers in Asia. We also have an entity in China. We are looking at staff there now. It's a little bit complicated because of COVID and because we cannot travel there, but we're looking forward to ramping this up significantly over the course of the next couple of months as these COVID restrictions are hopefully getting lifted. We have established some initial staff in China to serve our customers there. And we are very, very excited about the future there. Also Japan, Korea, all of these countries are of very, very high interest to us. And we have our first initial customers in these.
Yeah, that's great, Lin. Good to know about your plans about Asia and how your technology will revolutionize and change a lot of how manufacturing is done in the region. So what does the future of manufacturing look like with the convergence of AI and additive manufacturing going ahead?
Yeah, so the future of manufacturing is something that excites me a lot because, almost everything around us is manufactured, right? So any changes there, any dramatic changes there will have dramatic effect on our lives. And we need this dramatic effect. As I said earlier, we are kind of running out of time with some of our global issues. And as Diana Figueres said, the architect of the Paris Agreement on Climate Change, the fourth industrial revolution is what is going to solve this. Nothing else can solve it. Nothing else is fast enough to actually give us the innovations that we need now to solve this. So additive manufacturing has long been treated as kind of a stepchild of manufacturing. It was used for prototyping, it was used for small production runs, it was used for very small experiments, usually relegated to the innovation projects of companies. This is all changing. If you've been to any of the recent trade shows, Formnext, 2 years ago, it was all about the industrialization of AM. So currently, additive manufacturing is all done in boutique factories. You have people running around with vacuum cleaners and taking stuff out manually, depowdering it manually, whatever. There's a lot of manual work. But if you go to a BMW manufacturing plant, you don't see a lot of people running around, with vacuum cleaners and holding stuff in their hand. It's all automated. So what we're going to see in the next months and years is more and more automation coming to AM, and that enables digital factories. Now, these digital factories will not have many workers inside, but they will be highly flexible. They will be integrated. There will be a lot of different processes integrated. So additive manufacturing is not just the manufacturing part in the printer, it's also the finishing, and making sure that there's actually a real object coming out that you could sell. So we are going to see a lot of the integration of these processes, and we are going to see a split between two trends. There will be highly decentralized factories that are relatively small, that can produce relatively universally. And then what you're also going to see is highly concentrated, super complex, smart factories that are not cheap, that are not small, and they're probably going to be centralized because they're going to be very expensive. So I think these are the two trends that are going to see, decentralized manufacturing very close to the consumer, and then centralized but highly complex, highly integrated. Maybe the microchip factories of today are a good indication of where this could go. Now, the interesting thing is that that's just the manufacturing part. That's the big enabler. The only thing that we are interested in as Hyperganic is mass manufacturing. When I say mass manufacturing, I don't say we produce the same objects all over again. I say it's a large number of objects that are going to be produced. So this is what we are driving, and this is what is going to happen in the next years. The important enabler on the design side is our new software paradigm, where we can design objects that have never been attempted before because their design and their engineering would have been too complex. So this is really, really exciting. When you have a software paradigm, you solve problems usually only once, and then you just reuse the software. In traditional software engineering, if you design a database, then you can just from now on use the database. Other people can use the database. What they use the database for, whether they use it for a social media platform or for tracking flights or for doing a customer relationship management, doesn't matter. It's a database. If somebody builds a better database, they can just plug it in, and now this thing works faster, better, whatever. So you invent things only once. Now, if you move that to engineering, it means you can invent things once and then everybody can use it. And there's going to be open source things, there's going to commercial aspects of it. But fundamentally, the big transformation is that people solve a problem only once and then everybody can use it. And if a problem can be solved at a little bit better, then everybody can move very quickly to this better solution. So this is how innovation in IT works, and this is how innovation in engineering is going to work. And these two elements together, you have a software-driven engineering approach that comes up with highly optimized and highly innovative new objects all the time. And this coupled with a flexible manufacturing process where objects can actually change, and it doesn't matter because the printer doesn't care whether it prints the same thing or a different thing every time. This together is going to be a gigantic enabler for breakthrough innovation. Currently, with traditional manufacturing, you're not only hampered by the tools, you're also hampered by the fact that you have to build a specific machine for a specific object, and you're very highly disincentivized to change the design of the object, because then you also have to redesign the machine. And maybe you just have to redesign the tool, but it is still a lot of work. In additive manufacturing, your manufacturing process is very flexible. So whenever you come up with a new invention, whenever you come up with a new innovation on the design side, you can immediately implement it in practice. And this is really going to speed up things dramatically. And if you want to know how much it's going to speed up, then just look at Moore's law, just look at what happened in IT, just look at the last 20 years in computer technology. This speed is now going to manifest itself in engineering and manufacturing. And all bets are off how the world in 10, 15 years is going to look like.
That sounds great. I think that's quite a insightful thought and information for all our audience. And you spoke about Asia, and we hope to see India also feature in your plans, because India is a huge manufacturing base. So I hope to see you in India sometime soon.
Oh, absolutely. We do have some customers in India, and we do have some plans in India. We see India and China a little bit separate from Asia as a general term, because I think it's a very specific market, and you have to approach it in a very different way.
Great. So thanks, Lin, for joining us today and sharing your views about the future of manufacturing with artificial intelligence, and hope to see you soon.
Thank you, Aditya. So really enjoyed our conversations, and looking forward to the result.
Thank you for joining us for another episode of AM Infocast, powered by AM Chronicle. Do tune in next week for another new episode.